Hi, I'm Walid Krishen, and this is the NIPS Spotlight on acceleration and averaging in stochastic descent dynamics. This is joint work with Peter Bartlett at UC Berkeley. In this paper, we study dynamics for smooth convex minimization. We propose the first continuous time model of stochastic accelerated optimization, and we study the interaction of the noise properties and the parameters of the dynamics and their effect on the convergence rates. This work builds on previous models of continuous time optimization. We briefly review these building blocks. The first is mirror descent. Continuous time mirror descent is defined by coupling a dual variable z, shown in red, which accumulates gradients scaled by a learning rate eta of t, and the primal variable x, in blue, obtained by applying a mirror map to the dual variable. This mirror map is a map from the dual space to the feasible set, and can be thought of as a generalization of the Euclidean projection. The second building block is acceleration. In a previous paper, we showed that a generic way to accelerate for stored dynamics is to add averaging in the primal space. The primal variable x then become a weighted average of the mirror trajectory with weights w. The weights w and learning rate eta need to satisfy a simple condition given here. In particular, Nesterov's dynamics can be written as a special case of this family. In this paper, we study a stochastic variant of the same family of dynamics. The basic idea is to replace the gradient with a stochastic estimate of the gradient. The dynamics can then be described using this Ito stochastic differential equation. Here, B of t is an n-dimensional Brownian motion process, and sigma is a volatility matrix that can depend on x and t. We will assume the following bound on the norm of the covariation matrix sigma sigma transpose, which will allow us to study different noise regimes. When the gradient is noisy, one should be careful in applying acceleration. In this numerical example, if we simply apply Nesterov's dynamics to the noisy case, shown in yellow on this figure, the noise quickly accumulates and we lose the good convergence properties of the deterministic case in blue. But if we carefully choose the learning rate and averaging weights, we recover convergence, as in this red example. To shed some light on the interaction of acceleration and noise, we derive the following bounds on the suboptimality gap. In the deterministic case, the bound is inversely proportional to the integral of eta. In the stochastic case, we have this additional term, which intuitively corresponds to an accumulation of noise. These bounds are obtained by first defining an energy function, then bounding its variation. In the deterministic case, the energy is decreasing, but in the stochastic case, we have additional terms by Ito's lemma, which contribute to this additional term in the bound. The next natural question is what choice of parameter eta will give the best bound. This can be easily derived, for instance, if we have a polynomial bound on the noise. We verify these results experimentally on two examples here. The first example has persistent noise, in which case the optimal eta decays at the 1 over root t rate, and we recover the familiar 1 over root t convergence rate. The second example has decaying noise, and in this case choosing the right eta along with the right averaging allows us to take advantage of the noise decay, leading to a faster convergence rate. We have many more details at the poster, and we hope to see you there.